All right, good morning, good afternoon, good evening, whenever you may be. It's time for another exciting adventure into science here at Ace Academy. Live from the Brenna Bunker, somewhere in the quarantine Southeast United States, it's 7th grade science at Ace Academy with Mr. Brenneman. All right, glad to see everybody out there again. Hope you guys had a great day yesterday and hope you're having a good one again today. Doesn't matter what day it is in reality, but as long as your day's going well, we're doing all right. All right, so we're going to continue on with our Earth systems stuff. Today we get into clouds. Now, for a lot of people, it's like, clouds. I mean, they're just big puffy things full of rain up there in the air. Well, yeah, kind of, but yeah, no, not really, because guess what? The science of clouds is actually kind of pretty serious and intense stuff. So, but let's not get wound up with that. Let's just kind of go, all right, let's just get going with it, and we'll get into it. We'll run into where the craziness and difficult things are. But for the most part, we're not really concerned about it. But we just have to understand that we're really simplifying some things. So our I can statement today is I can explain how clouds form. So clouds are such regular and ordinary things in our lives that we tend to overlook them until they are providing a strong input into what we're doing. Rain, snow, hail, tornado, or hurricane. And yeah, we're all well aware of what the clouds are doing and what they're foisting upon us. But outside of those conditions, we typically don't give clouds much thought. But if we do pay attention to clouds, they tell us a lot about what's going on in the atmosphere at the time. And just remember right now, for our purposes, we're taking some very complex and elaborate mathematical systems and physical systems and simplifying them enormously. In fact, there's an entire course in college, if you want to be a meteorologist, that is all about how clouds form in the atmosphere and why. It's called physical meteorology. Offered at UNCC as part of their meteorology undergraduate degree, just in case you happen to be interested. Clouds are simply collections of liquid water droplets that have gathered in large enough numbers to become visible to the eye. Okay, fairly simple, right? Clouds come in all shapes and sizes. They're classified according to the height at which they form. You have low, like medium, and high. That's pretty much three areas which they form. And that's how we classify them. We'll talk about that tomorrow as far as the naming and classification of clouds. They can consist of liquid water or ice. They could be many colors or just somewhere between white and black, but for the most part, they form in the same way. And here we go. For a cloud to form, two ingredients have to be present: water and dust. Water gets in the atmosphere as a water vapor, a gas. Remember that the water cycle evaporation takes liquid water and turns it into gas, right? On the Earth, the atmosphere can contain anywhere from 0 to 4% water vapor. Well, if you have 0% water vapor, do you think you'll have a cloud? No, not going to happen. But at 4%, yeah, the chances of getting a cloud are pretty significant. Nietzsche? No. So the other ingredient is dust. The air must be dirty. If it was pure air and there wasn't anything in it, clouds would not be able to form. If clouds were able to form, guess what? We wouldn't be living the way we are today. It would be a vastly different planet. But luckily, dust gets into the air from many different sources. So, between volcanoes, pollution, smoke, salt from sea spray, and sand and dirt blown up in the sky by the wind, there's all kinds of dust particles in the atmosphere. And for the purpose of clouds, these dust particles are called condensation nuclei. There's our first big fat word that we kind of need to pay attention to today. Condensation nuclei. Nuclei, right there. Nuclei. Condensation nuclei. So basically, these are the dust particles that are in the air, floating around, that are what the clouds form on. Once we have these two ingredients, then we need some appropriate conditions. So got to have water, got to have condensation nuclei or dust. So, but first we're going to address how we refer to the space in which a cloud will form. And again, yeah, no, I mean, we keep going on like little side things going this way and that way. But yeah, but we do need to do this because, again, the terminology, we got to have the right terminology, and then have the right terminology, we got to understand what we're saying. So in meteorology, the air mass a cloud forms in is called a parcel. Why is it called a parcel? It relates to the mass of air being treated as a fluid and how it moves and reacts is explained by the physics discipline of fluid mechanics. Again, fluid mechanics, another one of them college courses that if you do engineering or something else like that, or meteorology, you will love to hate. But anyway, let's just suffice to say it is a physics discipline called fluid mechanics that is very, very mathematically involved. And the math behind cloud formation is deep. It still has literally as areas that are partially or wholly unexplained to this point. It is an active field of research. We don't know everything there is to know about it yet. So we're still working on it. But for the most part, especially controlled situations, we understand what happens. So going forward, we'll refer to this mass, referring to the body of the air, not really the amount of matter that a cloud forms in as a parcel. So we have a parcel of air that's somewhere near ground level. Due to the sun, which drives all water cycle activities with its energy, evaporating water off of a lake, this parcel contains water vapor. Parcel is blown over some freshly plowed fields. And when you freshly plow some fields, especially where the earth is incredibly rich for growing things, that dirt tends to be very dark. When you go buy dirt at the Home Depot or Lowe's in the bag for your mom to put a plant in or something, when you open that bag up, what color is that dirt? It's really dark. Well, if you have a good field for farming, when you turn over the dirt, it looks the same way. Very dark. Dark things do what? They absorb energy from the sun, much better than light colored things. So now we have this dark colored patch of ground, which is absorbing lots of energy from the sun, and our parcel of air wanders across it. Well, the bottom of our parcel of air is in contact with the ground, and though through conduction, remember things touching each other, the air molecules are physically touching the ground right there at the bottom of the parcel. Those air molecules pick up the energy from the ground and carry them up into the rest of the parcel, and as they bounce around, they transfer that energy around. And the next molecule comes down, runs into the ground, picks up some of that energy, and runs back in the cloud. That's how the heat gets conducted from the ground into the parcel of air. So as the molecules in the parcel move around, they transfer this energy throughout the parcel, and the overall temperature of the parcel rises. Now remember, adding water vapor already makes the air parcel less dense. We talked about that the other day. What makes air pressure go down when you add water molecules? That's one of the things, because water molecules weigh less than the oxygen molecule or the nitrogen molecule that it likely replaces. Remember, our friend Avogadro says in any given space of air, you're only going to have a certain number of molecules in it at a given temperature and pressure. So now, we're changing the temperature and et cetera, et cetera. That's why these things are so complex and mathematically hard to play with, because again, all these things are constantly changing, but again, trying to be simple. So now we're adding water vapor already makes the air particle less dense. Now we're adding heat energy and become less dense still. Less dense air has less gravity acting on it, lower gravitational effects, and the parcel rises up into the atmosphere. This is only one really reason that parcels rise, but this is what we're going to talk about today. So now we have a parcel rising. So remember, as we go up in the troposphere, the temperature does what? It goes down in the troposphere. Remember, divisions in the atmosphere based on what? Oh yeah, it's where the temperature goes one way and then it starts going back the other way. Oh, there, we'll call that one of the divisions. So in the troposphere, the air temperature goes down as you get higher in the atmosphere. Why? When you go up in the mountains, they have snow on them. Well, as down in the valley, it's nice and sunny and there's colder, higher for the troposphere. So our parcel of air, because the troposphere is where all the weather happens, so you're not likely to get clouds above the troposphere anyway, especially cloud formation, except for a couple of things. And guess what? This is science. There's always one or two exceptions, right? So now we have our rising parcel. So then go up in the troposphere, the temperature goes down. And also remember that the air pressure goes down as well. So our parcel wants to reach equilibrium. Equilibrium is one of them scientific terms. It means I'm just like the next guy. So things in science, things in nature always want to be like the thing next to it in energy and things like that. So that's equilibrium. This means it wants to be like the air around it in temperature and pressure. So we have a rising parcel. It experiences less pressure from outside of it, lower air pressure. In order to equal itself out, the conditions to the outside of it reach equilibrium. It expands. As it expands, the actual pressure inside the parcel goes down. We'll because I mean, we're not adding many more molecules to it. So we have a larger box effectively for the same number of molecules. And so they'll be pressing on the outside of the box less because there's fewer of them running into it, lower pressure. So our parcel is also warmer than the air outside of it. It wants to cool off as well as reach equilibrium with the air outside of it as far as temperature goes. So now our parcel is getting larger and cooling off. As it does this, the amount of water vapor, the physical number of water molecules in it, stays the same. The air can only contain so many water molecules, especially certain temperatures and certain pressures. It has a limit to what it can hold. This limit is termed saturation. There's a word we need to remember. We also need to know equilibrium. Let's go ahead and mark that one too. So saturation. At saturation, the air is holding as much water vapor as it can. And for any given mass of air at a certain pressure and a certain temperature, you can calculate exactly how much water is in it at saturation, but we don't really need to know that at this level. But just refer to say that it's got all it can hold. The bucket is full. At saturation, the air is holding as much water vapor as it can. We also refer to the amount of water vapor in the air as humidity. You guys have probably heard that one. So humidity. So when we talk about humidity, humidity is not an amount, but a percentage. It's measured this way because the amount of changes with pressure and temperature, like I just said. So at saturation, the humidity is 100%. It's got all it can take. Can you have 101% for real? Not really. Our parcel has expanded due to lower air pressure, is cooled due to the decrease in temperature of the air outside the parcel, because again, it's still going up in the atmosphere. And now it's finally kind of reached equilibrium as far as temperature and pressure goes. And it has reached the saturation level because it still has the same amount of water vapor in it. Next, the parcel either experiences another drop in pressure or temperature due to continuing to try and get to equilibrium. So it's either going higher or it's getting bigger. So getting bigger means the pressure goes down. Getting higher means the temperature goes down, or both. So parcel is already saturated. It can't, it's the temperature's gone down. It's reached the point where it's got as much water vapor it can hold as a gas. And then something has to change because some things are always moving to be in equilibrium. Things that change is the parcel becomes supersaturated by about 0.1%. You hit that 100.1, 100.2% saturation level, supersaturated as it is. You are beyond the carrying capacity for that mass of air of water. Now those water molecules in that supersaturated parcel of air are just looking for any reason to get out of being a gas. So they really want to be a liquid very badly. And then here's where that dust plays a part. So those water vapor molecules want to be a liquid very badly. The dust particle comes along and they just jump on it. So that gaseous air water vapor molecule suddenly goes, oh, there's a piece of dust, and it condenses on it. Just, hey, seizes the opportunity that presents itself by the dust particle coming by, and the water vapor molecule switches back to a liquid and condenses onto this piece of dust. Now, again, when we talk about this happening, it's like the 0.0002 size, thing, the little bitty droplet of water. I was having a droplet. It's something so small that we really can't conceive of. But 0.000, is really small. And they're actually, for any given piece of dust, and again, piece of dust is really small, there may be hundreds of actual droplets of water condensing on it, on the outside of it, because these droplets are very, very small. But when you get a bunch of them condensing onto this little piece of dust, it does increase the size of it, significantly enough, and you get enough of them doing it. And this is where you get a cloud. Now that the level in the atmosphere that this is occurring at is called the cloud base. Now that these dust particles have some liquid water drops on them, we can see them. They reflect sunlight, and we perceive this reflected sunlight from these little condensation nuclei with water droplets, little bitty micro droplets of water on them. So we see as a cloud. So here's a little bit of a thing to kind of show you. So at the surface, here's our parcel. And it's just giving numbers. Temperature 30, the dew point, which is again, another name for the amount of water in that parcel. And it's the temperature. Dew is when you walk out in the morning and there's what? Water everywhere on top of the cars, on the grass, because that dew settled, saturated, settled out of the atmosphere because of the change in temperature. So we walk up, we go from here to the surface, the temperature's coming down, the dew point stays the same at 18 degrees, because we're still talking the same amount of water. We get up here to this altitude, you notice, so that small box, then we got a medium-sized parcel. Now our parcel's pretty good sized, gotten larger because the pressure pressure's going down. So the air pressure that was in the parcel makes it expand, so it's gotten big. So this is the same number of air molecules, but the space they occupy at this point, because the temperature has gone down and the pressure has gone down, is larger. And now here at 1,200 meters, our temperature has gotten down to the point where it's 18 degrees, which is the dew point. The dew point's based on the physical amount of water vapor that was in that parcel. So the dew point of if it had more water in it, that dew point would have been higher. Had less water in it, the dew point would be lower. This parcel had to go farther up in the atmosphere, cool down more, expand more before a cloud would form. But once the temperature and the dew point hit the same number, that's when those water molecules are supersaturated, and they want to get out of being a gas and go back to being a liquid water. And they jump on those little dust particles, and that allows us to see them floating around as those big puffy white things called clouds. So I can explain how clouds form. A parcel of air has evaporated water vapor in it as part of the water cycle. It rises due to four different things. One of the things is convection, conduction, convection. Rises just like a water balloon, hot air balloon rises. As it rises, it expands due to trying to reach equilibrium with pressure. It cools off, because it tries to get the equilibrium as far as temperature with the air outside of the parcel. And as it does this, the humidity increases in the parcel until it reaches 100%. And once it reaches 100%, it's saturated. And once it's saturated, at that point, any further decrease in temperature or decrease in pressure and decrease in temperature pushes it to supersaturation. And once it hits supersaturated, any little dust particle wandering by those supersaturated, water vapor molecules, they will condense out of the air onto that piece of dust and go back to being water. Oh, and by the way, when things change like that, when you change state, guess what? You give off a little bit of heat. And when you give off a little bit of heat, guess what it does to the cloud? It makes it warmer again and drives that mass, the temperature of the mass, of the parcel, makes it a little warmer, which makes it what? Rise a little further. And then it returns to supersaturation and more water molecules condense out. So it's a kind of a self-repeating process until you get a pretty decent sized amount of cloud. And then finally it reaches equilibrium, because now the cloud is formed, gets enough water out of the vapor out of the air, everything kind of evens out, and it reaches equilibrium. So now you have a parcel of air that's now basically the same as the air around it, and you have a cloud. Now remember, check in the video, bottom of the video, say hey in the comment section. That's the how we're taking attendance these days. Remember, remember to like our channel, excuse me, subscribe to the channel, and give a good thumbs up, like to the video, please. If you have any questions or anything, please ask. Call me, 704-363-9034. Text me, either one. Remember, please get a hold of me. If you say something or leave a question, something in Google Classroom, whatever, and I don't respond within about 24 hours, the same time the next day, use a different way, ask me again, okay? So, any questions or anything, please let me know. Please check in on your assignment. You should have a set of questions for today. Hope you have a great one, and we'll catch you next time.